Hello and welcome. Today's webinar is on how to effectively use certified equipment in fire and gas systems. This will be a multi-part series, and today we have had the privilege of having a guest speaker, James McNay from Micropack. He's one of the leading experts in fire and gas, and he is going to be with us today. My name is Ted Stewart. I am the Program Development and Compliance Manager here at Exida. I have about 10 years of experience in safety and high availability automation systems and manufacturing and in lean process improvements. My previous occupations, I was working for a Lockheed Martin in missiles and fire control as a test engineer. I went over to a communications side as a manufacturing lead, and then a new product introduction manager where I was working for Harris Corporation with a few different clearances. And then I came over to Exida because I was really into safety. I loved a rewarding job. I now manage the OEM certification division. I'm the deputy quality manager and also the director of the CFSP program. And the next individual, it does give me great privilege and pleasure to introduce our featured guest speaker, Mr. James McNay. He's one of the leading fire and gas experts who I had the pleasure of meeting at an ISA committee meeting. Mr. James McNay, go ahead and introduce yourself.
Thanks, Ted. Much appreciated. My background, I'm currently the operations manager at Micropack Engineering, based in Aberdeen, in sunny Scotland. My background is more in civil fire safety engineering, or before my time in oil and gas was in civil fire safety engineering, looking at performance-based fire safety design in buildings, high-rise flats, high-rise hotels, quite unique infrastructure from more of a civil basis. In 2010, I moved into oil and gas. The background in fire safety was fairly relevant for some incidents we've seen in oil and gas in the not-too-distant past. The first thing I noticed in oil and gas was that fire safety is relatively underdeveloped and still fairly prescriptive. What I primarily do in oil and gas is design fire and gas detection systems for any kind of hazardous application, whether that's onshore or offshore. Design fire and gas systems for most of the oil and gas majors around the world. I've been fortunate enough to be involved in the generation of a lot of the prevalent fire and gas guidance documents that are available in the industry. And I'm currently the Fire and Gas Chair of the ISA Safety and Cybersecurity Division. So that certainly keeps me busy, keeps me at the front end and on a lot of the methodology developments, probably my favourite part of my role, to be honest. So I'm looking forward to presenting on fire and gas detection.
Thank you so much, James. I really appreciate that. And one more time, I do want to thank you for being on today's webinar. Really looking forward to your part of this series here. Let's go ahead and continue. As with most of our webinars, if you guys do have a question, you would like to ask something, if we're not answering it right away, there is that questionnaire that you can go ahead and type it in. If we can get to it, we will. If we can't, we'll wait till the end. I know the first series we did have some great questions. And I'd like to start off by, because we always have some new faces on here, do a few quick slides on the introduction of Exida, and we'll get right into the presentation. If you do not know, Exida, we were founded in 1999 by some of the world's top reliability and safety experts, Dr. William Goebel from the United States, and also Rainer Fowler from Germany. So that's where our two headquarters lie, and you'll see all these other red little dots. I think we have a new red dot every year in another part of the world where we're rapidly expanding. Last time I was telling everybody Japan was our fastest growing, but now it looks like our new division in India is going to start taking off rather quickly. Exida is involved with the complete supply chain of functional safety in multiple industry sectors, from the original equipment manufacturers who require the product certification all the way to the end users that use that product. Now, Exida, we provide software tools, we provide training, consulting, and procedures related to functional safety, security, and reliability. As you see here in front of you, we do have a suite of products and services, whether it be consulting and 61511, which is for the end users, and 62061 for machinery, 26262 for automotive. We have alarm management, we have cybersecurity, 62443. We do engineering tools, which have been extremely helpful to me. I've been here for about 5 years at Exida, and I'm just now getting into the engineering tools, and I can't believe I didn't use these sooner. It's so nice having a software program to do things for you. I focus most of my energy in product certification. We have training programs. We usually have one training somewhere in the world once a week. Reference material. We have been known to publish everything we can because we like to be an open book. Anything we know, we like to share it with you. So there's nothing there that you can't do either. And of course, product certification or personnel certification, which has been a much higher demand now that IEC 61511 has stronger verbiage in there requiring those requirements. All right, so today we're going to talk about how to use product certification. When you get a product certified, how to use it effectively, right? Because it's one thing to get it certified, it's another to use it in the correct system. And I'm going to have James McNay, who's going to help me with that part of the presentation. But to get things moving, we thought it'd be helpful to kind of share with you, okay, well, you know, how do I even get started? Okay, I get that you want to use it in the right system, but let's first talk about, well, how do we get that product certified? And then we can talk about, okay, how do you use it in the correct field? You know, where do I get started? What do I need to get started? Do I actually need certification? This is why our first step with any customer is, you know, we want to first chat with them. We want to talk to them. We want to answer any questions they have about getting certified and determining if certification is even right for their application. If it is, you know, then we can go over the process and the expectations for the project. We can review the project. We can review their bulletin. We can have them fill out an application. And this is where, on that application, you can start learning about them. You know, you can say, hey, is this going to be one valve, or is it going to be a family of valves? Is it going to be one FMEDA? Is it going to be proven in use? What type of product is it? Is it type A, or is it a type B product? And all of these questions and clarifications get answered ahead of time. Now, the beginning part of our process is, you know, the Exida IEC 61508 certification program. It offers the most comprehensive product review of any certifying body, and we do that on purpose. We have found that being comprehensive has generated results in products that are safer, more secure, easier to use, and more reliable. And now Exida, we operate this IEC 61508 functional safety certification program. We base it off a scheme. So we have a bunch of advisors that are end users that help keep us up with the latest trends, let us know what they see in the industry, so that we can morph and change our certification process to best suit their needs. Okay, now looking at the screen in front of you, you're going to see a snapshot of steps that a customer would go through when requiring certification. You know, the first thing you do is you have that kickoff meeting. Let's get everyone going. Let's figure out the agenda. Let's figure out who the point of contacts are going to be. Then in parallel, we're going to be working on two different things. We have one engineer that's going to be assigned to do the FMEDA analysis, which is a calibrated FMEDA. And then also, we're going to have someone working on the safety case, which is looking at your design documents, your product documents. There's two parts of that safety case. There's a baseline and there's a final. And we have many other webinars to go into detail on these topics. So we'll keep it very high level, and we can point to those at a later time. And sometime during that project, you'll see here, we will come on your facility, we'll take a walk of your manufacturing floor, we'll ask some questions, we'll interview quality, and we'll make sure that we have a good feeling, and we can check the box to let them know that you are compliant to these standards. A couple milestones while you go through those steps is one thing that we're going to be doing is we're going to make sure that we meet the PFD average for the SIL that you have targeted, whether it's a SIL 1, SIL 2, or SIL 3. You know, we're going to look and make sure we have the low failure rates. We're going to look for those high diagnostic coverages. Also in hardware, we're going to look to see what part of the standard are we going to use to certify you, because there's many options on certification. You can have proven in use with changes, proven use with no changes. You can have a new product where you have no proven in use. And all these ways are fine, but there's different ways of doing the certification. Software, if your product has software, if it's a smart device, you know, we're going to go through software process requirements for that SIL level. If it's, and when we get to your product, we want to make sure the product have the process requirements in place as well with the documentation. And then finally, you're going to have that safety manual. Okay, so as I said, there are two critical steps in certification. You have the safety case and you have the FMEDA, the FMEDA. So the big question is, how do we justify, because IEC 61508 is so large, but how do you justify that you meet those requirements? Well, exida, we prepare a safety case for each certification project. A safety case is a complete list of all the requirements of the stated scheme, along with, as you see in front of you, the arguments and evidence that the product under the assessment meets all of those requirements. It is an essential tool to ensure completeness of the certification audit, thereby finding any potential dangerous flaws in the product design. And you'll be surprised what we could find in the short amount of time that we can do this, and only because we do it every day. Now, despite the proven value of this technique, there are actually few certification agencies that will actually prepare the safety case for you. Now, why do you think we insist on performing this safety case and also that FMEDA for you? Well, think about it. I like to bring this up because many people like to cut corners. Many people try and make sure they get things done quicker, not to their own fault, because they don't understand. Now, in a court of law, let's say something were to, an accident were to occur, and they're saying, hey, this was a certified product, it was supposed to be based off this standard, but it failed, and it wasn't supposed to. How can you justify in a court of law that you did everything you were supposed to do and you were compliant to this standard? Do you feel comfortable yourself, even though you don't do this every day, with developing such a safety case? Are you sure you provided evidence for everything? If you are, great. Keep doing what you're doing. Same thing with the FMEDA. Are you comfortable that you use the right database or you use the right methods that you could defend yourself in the court of law? Because we all know it's one thing to get certified. It's another cost when an accident were to occur. So the second critical step is the FMEDA. One note I do want to mention here is that not all FMEDAs are created equal. You know, you want to ask those questions if you are an end user. You know, who performed this FMEDA? Where did they get their database? And is this information in the database from the process industry? Because we've seen many FMEDAs that were done based off of consumer reports, off of military, or even telecom industries. Because if you've already put bad data in, you're going to get the bad data out, right? I have one question here. Sorry, I just want to sidetrack so I don't take Andrea's time. Yeah, the morning and the afternoon are going to be the same webinar. Part 2, I'll make sure I get you that. But yes, these are going to be the same portions. Okay, so now with the calibrate FMEDA, the difference here and what a calibrate FMEDA is it basically takes realistic or your estimated results and your predicted results, and they make sure that the two relate to each other. So when you take real field data out in the industry and then you take your predicted results, you want to combine the two to make sure they match. If they don't, you're going to keep looping to figure out, okay, where were they off, and you're going to calibrate the FMEDA and make sure that the predicted results are showing how the actual results are. Okay. Now with all these different steps, right, all these items we spoke about, they're all necessary. They're all required for this certification. And all these steps must be complete or that product is not certified. And that's very important because many people feel that they only have to do, hey, I'm just going to do the FMEDA and I have the failure numbers. That's all my end users need. So this is good to go. I have that certification. Now the end result of the certification process is that certificate and that report. The certificate lists the SIL level for which that product is qualified. Now, however, it must be understood that products can receive a full certification with restrictions, okay? So with these restrictions, make sure that when you have the certificate, look at that safety manual to see what restrictions are even listed. Another thing I want to point on here, and we'll move forward, is that notice that there's two signatures on this certificate. You have an evaluating assessor and a certifying assessor. The evaluating assessor is the person that does the bulk of the work. They actually go through the whole certification process. They meet all the requirements. They do the safety case for you. The certifying assessor is someone completely impartial to the actual work here. And what they do is they go in after the fact. They don't know anything. They walk in, let's just call it blind, and they do a second analysis on here to make sure nothing was missed. Right. So with an extra certificate, manufacturers, there's many benefits of having a device that demonstrates this high design, the quality from the third party, right? So there's a lot of qualifications and there's a lot of benefits to having it, right? Besides having the market recognition, where now a product that is certified can be on this SAEL website, which is basically where end users go to shop. There's links to that product that go directly to their sales department to answer any questions on that product. So the awareness and the level exposure is increased. And another great feature that many people don't think about is this Excellentia database. Now anything that got certified will get dumped into this database. So now when people are building their systems, they can click on, product X or product Y, and all the failure rates will populate automatically. And they can build systems, determine their SIL levels right then and there. And of course, getting it certified, you can actually enjoy reduced failure rates and design flaws due to the fact of our analysis. All right, two more slides here, then I'm gonna pass this over to our guest speaker, James McNay. And finally, when we do these types of certifications, there are some common questions that's asked, and I was told, hey, would you give me the top 5 when you go through certification? And so I quickly put them up here. The first one is, how much time does it take to get certified? Well, if you're not familiar, for us, we do all the work for your company. The expectation from your company is to be provided documentation and to answer questions when they come up. All right, we do everything else. Many other certification bodies actually make the manufacturer do the work, which will drastically reduce the certification costs. However, it's a huge burden on that manufacturer. I know Dr. Goebel, he recently just got a quote, or just got an email, and I quote, and they said, hey, look, we use company X the first time, and it took us over 600 man-hours to complete the certification project. Our sister company, they used Exida, and they billed only 60 hours of man time. So that's just one way of showing the differences that not all certifying bodies are created equal. Another question that we get, why does an Exida certificate have an expiration date when others don't? And how long is it good for? Well, Exida, we do require that product manufacturers undergo periodical reassessments, okay? And for us, it's usually 3 years. At that time, we have engineering changes, those are examined. Field failure history, that's reviewed. And development and testing process updates are also reviewed to be certain that the product still meets the requirements of the reference materials, right, and standards. Because we all know that people change within organizations, and sometimes things got in place, and the guy that comes into that role says, I really don't even know why it's in there. It's a little time consuming. Let's remove it and keep moving, right? So we want to make sure when we come, we look at those procedures, and we make sure that you're still meet the requirements, and that's why we do it every 3 years, because that seems to be the cycle time. All right, who authorizes Exida to perform these certifications? Which is always a great question, and we don't mind people asking us what says, hey, why are you allowed to do this? Well, IEC 61508, it's a standard that requires evidence of competence, okay, and of those who perform assessments, but does not require that they're formally authorized or accredited. However, most end users who purchase IEC 61508 certified equipment, they are now demanding that certification is done by a high competency technical organization with, this is the critical point, that's accredited by ANSI or any other accredited body per the IAF. IAF is your International Accreditation Forum. What that means is, look, we want the certifying body not only to be held liable by an accredited body, but certifying body, us, be accredited by ANSI, but even them have to be accredited by someone even higher. So the hierarchy is huge, and the IAF is really that global provider who really looks over all the accreditation bodies worldwide. So what that means is, because ANSI is a part of the IAF, now Exida is a global recognized company. Okay, and that's how that works. Now, product certification programs, we operate per 17065 for lab, for product certification programs, and also for 17025 for the standard for test laboratories. Question 4, can I certify a brand new product or product? Well, yes, if it's a new product, you can. We do a design-based certification. If it's something that's been out there for a while, we do something what's called proven in use. Can I certify a whole family of products? Yes. Single or whole family are able to be certified. So what's next? So we get through this point, and this is where it's great that I will be able to introduce Mr. James McNay. So you get this thing certified, you spend money, you get a beautiful certificate, you get this product certified, you get it out there in the market, and guess what happens? It gets used incorrectly. And today, because we're going to be talking about fire and gas, I thought it'd be amazing to have Mr. James McNay get in here and talk about, look, when we're on an oil rig, you know, because you see this flame here, this was actually off the Gulf of Mexico after a natural gas well ruptured, right? It's in the shallow waters off the Louisiana coast, and it blew up. Now, how do you mitigate this, and how do you make sure that this doesn't happen, and how do you optimize your flame detector layouts? And I'm no expert in that, but we have somebody on the line that is. So I would love to give control to this presentation over to Mr. James McNay. James, go ahead and take it from here.
Thank you very much, Ted. I will take the screen. All right, can I confirm that you can see my screen now?
Yes, I can. Go ahead, sir. Thank you so much.
Perfect. Thank you very much, Ted. I appreciate the opportunity to talk to you all about fire and gas mapping today. So thank you very much, Ted, for the invitation to participate. I was just thinking this afternoon about that last slide that Ted showed about the incorrectly used certified product, and it actually made me remember a site that I visited a few years ago where, to give you a little bit of background, obviously a flame detector is an optical based device. It has to look into an area to try and detect a flame within that area. Now, I carried out a site survey to go and review the flame detector locations. This particular client had spent a lot of money on a SIL2 fire and gas system. Excellent. The first area I went into, I found a flame detector that was looking directly up at the ceiling of the module. That flame detector would detect absolutely nothing within that area. So it is absolutely crucial what Ted has been talking about. You know, certification is one side of the coin here. It's absolutely crucial to make sure our devices are reliable, but we need some way to determine where we place our detectors, what these detectors should be looking at, whether our coverage is acceptable, how many detectors do we need, verifying why we've placed the detectors in the locations that we've placed those detectors. So there's a lot to think about here after the fact of determining the reliability of our fire and gas system itself. You know, whether that's going down a SIL rating, that's a very robust way to do that, to make sure that the probability of failure and demand of these devices is as low as reasonably practicable. Now, when we look at where to place these devices, if we're talking about a building, for example, and touching on my background from a civil point of view, if we have a hotel, for example, we've got documents like NFPA 72, British standards, depending on where you are in the world. We have well-established standards of how to design the fire detection systems for these areas. As soon as we go into an external facility, which is a hazardous area or a hazardous facility, we do not have these well-established guidelines and standards to use to place our flame detectors and our gas detection systems. We do have a few guide documents from certain operators, and we'll come to that later on, but there certainly isn't an international standard. So when we're designing these systems, we need to apply a performance-based principle. We need to risk assess the area, determine what the escalation potential is, and design our system accordingly from there. And that will allow us to, one, achieve an optimized system. So we need to make sure that we're not over-engineering the system by placing loads of flame detectors and loads of gas detectors into the area that we're trying to detect. We need to get the optimal number so that we meet our criteria, whether that's target fire size or a target gas cloud, with the fewest number of detectors possible to try and keep project costs as low as possible. And that's one of the primary drivers behind fire and gas mapping. One of the second primary benefits of fire and gas mapping is to produce an audit trail. So another thing that Ted mentioned earlier on was the fact that things change. You know, so from a product certification point of view, it's perfectly relevant that exida would want to say, you know, every 3, 4, 5 years, whatever the time period is, we want to have a look at the product, we want to have a look at your returns, and we want to make sure that nothing's changed which has affected the reliability of that device. Now, the same thing happens on a process facility. We want to make sure that the process isn't changing over time, which it often does. we want to make sure that new equipment hasn't been brought online in the area which have changed the hazards within that area. So when we go and we review the fire and gas detection design, we need to compare it against what the principle was when it was constructed. If we have a fire and gas mapping exercise, we can very quickly and very easily look at the justifications that were in place when the fire and gas was designed and check and see if they are still relevant. If something's changed, we need to redo the system, maybe do a couple of alterations, minor alterations. If the hazards haven't changed, we can just tick the box and say, okay, your fire and gas system is still operating as intended and is still fit for purpose. So they're the two benefits of why we would even want to carry out one of these mapping studies. In order to carry out one of these studies, there's a lot of input required. There's a lot of documentation that we need to look through, and it can be quite laborious to essentially generate our performance target document. Now, the performance target document is a site-specific document that does exactly as it says. It's the targets that we want our system to achieve, our fire and gas detectors. Now, those performance targets will be specific to individual pieces of process equipment, individual volumes, individual geometries specific to that area. And we'll have two split sets of performance targets. One set of targets for the flame detection system and one set of targets for the gas detection system. So in order to develop those, we first of all need a performance standard or a guide. Now, as I mentioned before, there are three primary guide documents available. One of them is from BP, the group practice, GP 3085. One of them is from Shell. They have their DEP on fire and gas detection, fire, gas and smoke detection. And the third one is the ISA document, TR840007, which is guidance on the effectiveness of fire and gas systems. Now, these three documents are the most widely applied pieces of guidance with respect to fire and gas mapping. If another operator doesn't or isn't BP, Shell, or they don't want to use the ISA document, we would expect them to have a fire and gas philosophy of their own that would allow us to set the targets appropriate to their corporate risk philosophy. So that's the first thing that's required. Obviously, if the operator doesn't have that document whatsoever, as a company, Micropack can help them through that process, and we can essentially assist with industry best practice. But in order to actually develop those targets, we need to start looking at the area itself. So we look at the cause and effects charts to get an idea of what executive actions are present within the area. What kind of voting philosophy are we dealing with? Is it 1 out of N for alarm only, or is it 2 out of N with executive actions and blowdown and shutdown associated with that? We need to have a look at the fire and gas plot plans. Obviously, we need to have a look if there are preliminary layouts. Then it's useful to know where those preliminary detectors have been located. If it's an existing facility, obviously we need to know where the existing detectors are in order to assess if they are adequate in their current location. The detector specification is crucial as well when it comes to the mapping. Each individual fire and gas detector will have its own operating characteristics, particularly flame detection. A flame detector has a very unique field of view that it can see in the area and very specific detection distance. So we need to know exactly what detectors are installed or proposed to be installed and what sensitivity, because that will have a huge impact in the detection output and the coverage which is achieved. We also need to have a look at the process flow diagrams and stream compositions, or the heat and material balance sheets. Now, this allows us to get an idea of how risky the process is, and it will allow us to decide if we get a fire or a gas release within this area, how can this escalate? How severe an incident can we get from this area? And the reason for that is that you wouldn't want to have the same detection layout in a utilities area, for example, a diesel storage tank area, as you would want in your high pressure separation area. You would want different levels of detection within those areas. And the process flow diagrams and stream data can allow us to determine where the real risks are on the facility. And obviously hazardous area drawings are very useful as well with respect to where gas clouds could accumulate and where gas could credibly be released from. So where do we start specifically with respect to flame detection? Now, with flame detection, we want to assess a target fire size. That's always the crux when we're designing our flame detection system. In the high risk areas, we want to detect a small fire to prevent that fire from escalating and becoming a large fire. So within high-risk areas, for example, grade A, that you can see in the image there, the red bubble, that would be an area where we would want to detect a very small fire to prevent it from escalating. On the converse, on the other side of that, we have the low-risk vessel, and in that area, essentially what we're saying is the fire can grow to a larger size before we would want to automatically start shutting things down. So perhaps it can still be manually controlled. So what we're saying is the target fire size is directly linked to the escalation potential of an incident within that area. Now, how that affects the detection layout is through the inverse square law. Now, flame detectors, obviously with a flame detector, the bigger the fire, the further away that detector can be. So if we're targeting a large target fire size, that requires fewer detectors within that area, because an individual detector itself can actually see more of the volume because our target fire sizes are much larger. And obviously treating fires as volumes, this allows us to optimize the detection layout in those areas. With a high risk area, we're looking for a smaller fire. The detectors have to be much closer to the potential risk area, which means ultimately we need more detectors in those high risk areas. The next step in the process, once we've set our performance targets, and we've gone through the area and we've assigned individual target fire sizes for every piece of process equipment in the area, we then want to start mapping. We want to bring the 3D model into the software, and we want to start placing detectors in appropriate locations. You can see one such detector in the screenshot there in the background. These detectors, as you can start to see there, are very heavily impacted by obstructions within the field of view. So it's very important that the 3D mapping accounts for these obstructions and the shadowing cast by these solid objects within the field of view. It's very important to use the correct field of view, and we're going to look at this in the next slide. Each individual flame detector has a very unique detector field of view. We will look at that, as I say, in the next slide. It's also very important within the mapping software that we can account for all the different fire sizes in one single assessment. So if we've got multiple high-risk pieces of equipment, multiple medium-risk pieces of equipment, and multiple low-risk pieces of equipment, we want to be able to assess those all in the same fire zone. And that will allow us to achieve a holistic view of the coverage within that area. And it will allow the engineer to decide whether the coverage is adequate or otherwise, assessing it all in one go. As mentioned before, we've got 3 example technologies shown here, visual flame detection, triple IR, and single IR flame detectors. Now, this is not an endorsement of an individual manufacturer or model or technology, but purely to show you the difference in footprint between these technologies. You can see from the visual device, because they're camera-based, there's a full 90-degree, almost like a pizza slice style shape from that detector. When we move to the infrared-based detectors, they're very much more teardrop and bubble shaped. And the reason for that is that as you move off axis with a detector using filters within the wavelength that infrared detectors operate, you do start to get a loss in sensitivity. And if you've ever looked at data sheets for infrared-based detectors, you will notice that they're very much teardrop-shaped flame detector fields of view. And the cutoff is very specific to each and every flame detector. Each and every triple IR flame detector, for example, will be reduced in sensitivity to a greater or less extent than another triple IR detector within that family. So it's very important during the mapping process to model the exact flame detector model, manufacturer and model, which has been selected to be used. I mentioned earlier on about the inverse square law. As I say, this is the absolute crux when it comes to flame detection mapping. The inverse square law stands up to around about 640 kilowatts in radiant heat output. Beyond that point, and with fires larger than that, we start to get saturation of the sensors, we start to get a little bit of noise across the detector, and essentially the accuracy starts to drop off. And that's quite an important note, that it can actually be more difficult for flame detectors to detect much larger fires, which is something that, to be honest, could be covered in a webinar in itself, and we may in fact do that as one of the future webinars. But for the purpose of this introductory webinar on mapping, we use the inverse square law up to that point. And to be honest, around about 640 kilowatts is quite a large fire. With respect to these systems being mitigation based, we really wouldn't want to be setting our target any larger than that, because the fire is probably uncontrollable at that point. We want to detect before that point. So what you can see from the inverse square law is that as we double the distance from the device, if our fire is twice as far away from the device, we actually need that fire to be 4 times the size in radiant heat output to be detected by that flame detector. And that's why you typically see radiant heat output targets of, for example, 50 kilowatts, 100 kilowatts, 250 kilowatts, and so on and so forth, depending on the escalation potential within the area. And we'll also look at this when I show you the mapping software just shortly. The reason for that is that they tie in quite nicely with multiples of the effective viewing distance. When we talk about 50 kilowatts, that's very close to the FM3260 test fire, which is what most flame detectors are certified against with respect to the performance. So our footprint of the flame detector is to the FM3260 square foot N-heptane pan fire. Now that's approximately 40 kilowatts in radiant heat output. So when we talk about these different target fire sizes, they actually tie in quite nicely with multiples of that detection distance shown in the detector manual from the manufacturer. So you can see here, these are the 4 processes involved in creating a flame detection assessment. First of all, we have to bring the model into the software. This particular model is a very simplistic model of our test facility in Aberdeen. We've got a very small, humble test facility in our facility in Aberdeen, where we can test the different sizes of fires and actually assess different flame detectors' characteristics. So we bring our model in here. We've then assigned a couple of high-risk pieces of equipment and a moderate-risk piece of equipment within the 3D model, as you can see in stage 2. In stage 3, we then add the flame detectors that are on our test ground into the model, and then stage 4 is our flame detection assessment. And I'll go into that in a little bit more depth in the software. So I'm just going to come out of the PowerPoint and open up the software package that we use, Hazmat 3D, which Micropack developed. And you can see a crude oil storage tank here. This is a very basic example that I've been doing a bit of work on this week. Now, first of all, I'll show you the grades which have been applied. So this is a little bit of a here's one I made earlier. We've got a number of valves associated with the tie-in here. Now, these have been graded moderate risk because they're a credible source of release. You know, that's a potential moderate risk area. You know, we'd expect to see a leak, a potential leak from those valves potentially. So we want some flame detectors local to those valves to make sure that we detect any leaks from those. I've also assigned a low risk grade throughout the entire bonded area, which you can see is graded here. And then I've also graded the top, the floating roof of the tank as a low risk as well. Now, with respect to the detectors which have been added, we can see the first detector in the corner there looking directly at those valves. Now, this detector, for the sake of argument, is a Draeger Flame 5000. However, when I select the drop-down box here, you can see that we have a number of different manufacturers here. If the specific flame detector hasn't been selected yet, obviously you can use a generic-based flame detector with a generic radiant-based footprint. However, when I select some different manufacturers and models, for example the Detronix X3301, you can see the specific footprint associated with that detector, and you can see how different that is if I then change that back to the Draeger Flame 5000. Oh, there we go. And you can see that they're very different footprints. Now that's going to have a significant impact on the assessment that we run. So again, just to emphasize, it is absolutely critical that we use a software which has the accurate flame detector footprint. And just to show you the output of an assessment here, we've got the low-level assessment of the bund and the tie-in. and we have our percentage coverages here. Now, before I explain those percentage coverages, I'm just going to go into the grades tab here and show you our target fire size. Now, for the moderate risk, if we concentrate just on the moderate risk for now, I've set a target fire size for a detector to provide an alarm of 100 kilowatts. And for our fire for control action is 200 kilowatts. So what I'm saying there is that I want a detector to go into alarm when we achieve a 100 kilowatt fire. And I want to ensure that I've got coverage when it goes to 200 kilowatts for certain. So that's almost like that's the control action value for 2 out of n when we then get that 200 kilowatt fire within the area. So what we can then see from the coverage is that for the moderate risk area, which was the tie-in area, we've got 65% control action coverage with a fast response alarm. So we've got one detector detecting a 100 kilowatt fire and a second independent detector detecting a 200 kilowatt fire. And we then get our executive actions within the area. What the yellow represents, this 15%, this is sufficient control action, but with a delayed alarm. So what we have there is 2 detectors detecting the fire when it gets to 200 kilowatts, but neither detector are close enough to detect a 100 kilowatt fire because it's too small based on the inverse square law for both of those devices to detect that fire. Now we often have an orange coverage in the middle here, but in this particular assessment there isn't even trace alarm only coverage. But for the purpose of a full explanation, the orange coverage would be an alarm only, where we just get 1 out of n coverage. Only one detector can detect the target fire size of concern. The brown coverage is where we have only one detector capable of detecting within that area, and it doesn't detect the fire until it's larger than our target fire size. So that's essentially a late alarm. We want to detect the fire smaller than it would detect in that particular area. And the red coverage is very straightforward. That's our blind spot, our 0% coverage, any blind spots within the area. So when the engineer has run this assessment, they very much have to use some engineering judgment to determine whether the coverage is adequate or otherwise. The percentage coverages are there purely as a guide. Now, a lot of the time, the guidance documents will provide a target percentage coverage, but we would very much advise not getting hung up on those, because you could very easily have an area with 90% coverage, which is inefficient and not an efficient coverage with respect to flame detection. If you've got 90% coverage, but the 10% that's not covered is your highest risk, then that area cannot be classed as adequate, and you would need to look at relocating some devices to try and improve the coverage in the high-risk area. Similarly, if you had an area of, for example, this area, 65% control action coverage, now that seems very low, but when we look at it in the context of where the blockages are and the fact that we have 15% sufficient control action with a late alarm, I would look at this assessment and assess that as adequate. So that's where we need to be quite careful, particularly of certain auto-optimization claims, because auto-optimization would essentially try and hit a target percentage and would not use an engineer's brain to look at the area and decide whether the area is adequate or otherwise. So that's a very, very, very important point there. I will just go back to the PowerPoint now, and we're going to look at gas detection now. I'm going to move on to gas detection. Gas detection follows a lot of the same principles, but it's an entirely different philosophy. So it seems a little strange to say it's similar when it is fundamentally entirely different. When we have an immediate ignition from a gas leak, we typically, if there's pressure involved, get a gas jet fire. Our gas detectors are virtually useless for applications like that. Our gas detectors serve no purpose. Where our gas detectors are useful is when we have the potential for a delayed ignition, and that allows the gas cloud the opportunity to accumulate within an area, and that's when we want our gas detectors to come into play. The biggest driver with respect to gas detection adequacy is the blockage ratio and how the ignition will actually behave within a specific volume. So with flame detectors, we were looking specifically at individual pieces of process equipment. With gas detection, we're looking at the entire volume. We don't really care about individual leak sources unless it's very low pressure and we have the potential for a heavy gas hazard. But by and large, we're looking at entire volumes and where the gas can actually accumulate. And the biggest driver as to how we lay our gas detectors out is what size of cloud will present an explosion overpressure of concern. Now, typically that explosion overpressure is 150 millibar. However, that can change based on project blast walls and various passive fire protection, but 150 millibar is generally accepted as the threshold for pressure-induced damage. So we want to, in each individual area, find the sweet spot, the target gas cloud that will provide enough gas to reach that explosion overpressure. And this is determined by the congestion within the area. If we look at the graph on the left-hand side here, you can see the flame front passing through a congested region. And what's essentially happening there is the flame front is being pushed back by the equipment and the congestion within the area. And we start to get overlap of the flame front, which increases the surface area of the flame, which therefore increases the pressure. And as the pressure increases, as the temperature increases, the pressure will increase. Those two are absolutely fundamentally linked. So as our temperature increases, as our pressure increases, both of those are playing off each other and the flame speed accelerates through that congested region. What you can see from the graph is that as the flame front then exits that congested region into the unobstructed region, we get a significant deceleration in the flame front because there's nothing for it to push back against. And you can see that demonstrated quite nicely on the right-hand side there. We've got an area, case A, with congestion of 7 to 8 pipes, with the gas within a tarpaulin and ignited. And we've got a fairly significant explosion after 60 and 90 milliseconds. On the right-hand side, we've got congestion with far fewer pipes, almost half the number of pipes, and you can see the difference in the ignition behaviour. When there's less blockage, the flame front does not accelerate to nearly the same extent, and we have lower explosion overpressures. So applying that to gas mapping, we essentially need to assign a blockage ratio to determine what the explosion overpressures are going to be, and link that to a target gas cloud. And that target gas cloud then becomes our performance target for the gas detection system. It's important to remember that we're not designing gas leak systems. So doing dispersion analysis to try and find out where the gas will go doesn't really help us here, because the gas might always travel to one location, but it may not actually present a significant hazard. It's always important to remember that we simply cannot detect every gas release. We have to decide which gas releases are going to cause us a problem and make sure that we detect those gas releases. We also then have to have an appreciation for the technology that we apply, whether that's open path technology or point gas detectors, or perhaps some of the emerging technologies like wireless systems. Technology is certainly improving all the time in the fire and gas world. So similarly with the flame detectors, we have to import our 3D model. We need to assign our grades to that area. So what you can see here is volumes where a gas cloud of a certain size has been found to present an explosion overpressure. So within the software, these targets are essentially showing us we want to detect a target gas cloud of X diameter within those areas. So we then have to lay our gas detectors out appropriately. And you can see in this area, we've got a combination of open path gas detectors and point gas detectors littered throughout the area. And then we have our assessment here. Similarly with the flame detectors, we have our percentage coverages. Now the green in this instance is the percentage of the area which is covered with respect to 2 out of n. So where our target gas cloud will intersect 2 devices at the appropriate set point and provide executive action and shutdown. And the orange areas show any alarm-only volumes, where the target gas cloud will only intersect with 1 gas detector and give us just an alarm. Now, there's a number of factors go into this assessment, such as dilution factors, dispersion factors, and target gas cloud factors. Now, similarly as before, that could fill a webinar itself, and I think we probably will have a webinar on that topic itself. But for the introduction, I think the target gas cloud with executive action coverage for 2 out of n and alarm-only coverage with 1 out of n is probably a good enough introduction for now. You may also want to show some perimeter detection in addition to your volumetric coverage as well, though. And you can see that represented here. And what we tend to find is that that can be very useful for commissioning engineers from a practical point of view. When they're actually out on the facility, if they have a 3D model which shows them exactly where to place the devices, that can be absolutely crucial. And it can help reduce the potential of your certified equipment being used completely inappropriately, if you can actually see it in your recognizable 3D environment. So again, I'm just going to come out of the PowerPoint now and just go back to the storage tank application. Now, this isn't the best application to show with respect to gas detection because we wouldn't anticipate any explosion overpressures here. We wouldn't necessarily want to look for a target gas cloud because it's typically going to be a liquid pool which perhaps flashes off and starts to migrate to other areas. So where our risk is a gas migration hazard, we would want to apply a perimeter type system. And what I'm just going to show you now is the open path gas detectors which I added earlier to try and monitor for the gas migrating to adjacent areas. Now those adjacent areas, it could be non-hazardous buildings, it could be public spaces, it could be another adjacent facility that you wouldn't want your gas spreading into and migrating into. There's a number of different factors that would make you want to assign a perimeter gas detection grade. And as I said, when it comes to commissioning, it can be quite useful for the guys on site and the installation team to see exactly where they place these detectors. And just a little best practice note, with open path gas detectors, obviously these can be blocked by things within the field of view. They have separate transmitters and receivers. So you'll notice that one of the open paths is slightly higher than the others. And the reason for that is to make sure that our walkway there doesn't block the open path gas detector. Now, people may walk back and forth and cross the beam, but we're not too concerned about that because with open path gas detectors, you can install a time delay, which means that something would have to block the beam for a certain specified period of time, for example, 10 seconds. So you would have to have someone standing at the top there for 10 seconds, and then the detectors fundamentally fail safe. It will provide a beam block fault to the people in the control room to essentially send them to go and investigate. Or the person will move on and the beam block will clear. Okay, so at this point, I will hand back over to Ted and thank Ted very much for the opportunity once again to present. It's been an absolute pleasure and I'll be happy to take any questions that anyone has.
Fantastic. Hey, thank you so much. I do appreciate that, James. That was some great information. I look forward to doing some future webinars with you as well. I think you brought up some great topics. Now we're going to open up the questions. I see a few here already. I'll go ahead and read through them, James. It looks like most of these are going to be for you. So let's start with the first one. Okay, the first question is, has this technology been applied to solid combustibles such as waste?
So yeah, so waste and recycling facilities have applied fire and gas mapping. What I would say is the real beauty of performance-based design is that it doesn't always have to be significantly complicated. And the waste recycling and storage facilities that we have carried out projects on, the performance target phase is very straightforward. And generally we would use a single target fire size that would be appropriate to the risks, and then we would apply the mapping on the back of that. So certainly the technology has and can be used in those applications. Yeah.
Fantastic. Thank you so much for answering that one. The next question I have here, and I'm going to let you answer this one only because people might think I'm biased, but they do ask, if we use the detector software correctly, do we even need to use a certified detector? James, go ahead and answer that one.
Yeah, that's a great question. The answer is absolutely. There would be no point in doing one without the other. What I mean by that is that within the fire and gas mapping, when we map the areas out and we get our percentage coverages and our pretty pictures, there's an inherent assumption that the detector will operate when it's called upon. So we're not accounting for any well, we do account for some desensitization, but we're not accounting for the detector being blocked by an issue with the electronics, for example, and there's a fire burning in front of the device and it can't see it because there's an error, and there's a probability of failure demand there. Our software and analysis doesn't take that into account. So there would be no point in carrying out that mapping if you've not certified your device, and there would be no point in certifying your device and then not carrying out mapping, as we discussed earlier on. So there are two sides of the same coin, and they're both absolutely critical, and I would strongly recommend that they're both carried out.
Fantastic. All right, thank you for that. Let's keep going on with these questions. Great questions, everybody. The next one is, how much detail can these layouts go into? And I think they're referring to the software. Are they only for oil rigs?
No, the software is not only for oil rigs. And where that question's come from, I know that the methodologies associated with fire and gas mapping, and fire and gas mapping itself was born out of offshore oil facilities. Micropack were involved with BP and Shell back in 1989 to develop the first fire and gas mapping tool, and that was primarily for application offshore. Now, recently, onshore facilities and even moving outside of oil and gas, we've had distilleries, waste recycling facilities, airports, aircraft hangars, all see the benefits of fire and gas mapping, because it allows that audit trail, and it allows you to know that the number of detectors you've specified is appropriate for the facility and the risks that you have on site. So it came from oil rigs, but it's certainly not just applied to oil rigs anymore.
All right, well, fantastic. I see here 3 final questions. If you do have another question, go ahead and enter them in. We'll try and get to all of them, but we are running out of time here, and I want to make sure everyone gets going where they need to be. But 3 last questions here. Can you recommend standards to help to develop the performance target which are application specific? Excuse me.
Yeah. So in the industry, we have 3 primary performance standards. I would say, they're more engineering technical guidelines. And that's BP's guidance, Shell's guidance, and the ISA document. They're the most prevalent guidance documents, and what they provide is guidance on how to set the targets for the specific application. So they'll talk about analysing the risk, analysing the escalation potential, and setting an appropriate target fire size and target gas cloud. I would advise those as the go-to documents.
Great. Okay. Another one here. There are various risk categories, high, medium, and low, within the same area. Hence, the target fire size will be different. How does it impact the number of devices required to achieve the coverage?
So that's fundamentally performance-based design. And yes, most areas will have high, medium, and low risk pieces of equipment within the same fire zone. And it has a significant impact on how many detectors and where you want to locate those detectors. We're long past the days of just placing detectors in the corners of fire zones to look at the whole area. And assigning high, medium, and low risk grades can reduce the detectors in some cases, but what it does do is it makes sure the detectors are in the right place and that you've got the correct number of detectors based on the risk. So it does have a significant impact.
Okay, thank you. And finally, is the software available, or is it? This is a good one for you. Is the software available, or is it only for Micropack internal use when providing fire and gas mapping assessments?
The software is completely commercially available. You can license it on short, medium, and long-term licenses, and perpetual licenses, so people can buy the software if they so wish. And Micropack are always willing to support as well. A license to the software we don't just give the software and say good luck. We support all of our software throughout the world.
Fantastic. That's great to know as well. Well, that is all the questions for today. If you're looking to learn more about that software, there are some classes there. You'll see there, Fire and Gas Detection Design and Technology. That would be on how to use this software and to learn about that technology. There's also other courses here. There's one in Houston, Texas, but this one's on Fire and Gas Detection Design and Technology. Oh, same course. And of course, there's some alarm management in the future as well. So if you're interested in training courses, please go ahead and check those out. If you have more questions for us, by all means, please go ahead and send them our way. Topics for other webinars, see at the bottom of your screen, academy@exida.com. I personally just want to thank you, Mr. James McNay, for coming onto this call today. It has been fantastic. I know our listeners are also pleased that you were able to join us, and I look forward to doing more webinars with you, sir.
No, you're very welcome, Ted, and thanks everyone for your attention, and thanks for having me again. It's been a pleasure.
Cheers. Thank you so much. Take care, everybody.